This overview is going to be on the special senses with focus on the eye and the ear. And when we think of the special senses, we typically think of seeing or vision, hearing or auditory sensation, smell, which is olfaction, and taste, which is gustation. Some textbooks may also talk about tactile sensation. In other words, being able to feel and manipulate our environment with sensors in especially our fingertips. So those are our special senses. Now, general senses are going to be, just as the name implies, more general, not as specific, not able to take in as much information from the environment, and giving us a view of what's going on in our outside world as well as our internal world. For example, a thermoreceptor. If this was a hot stove I was about to put my hand on, a thermoreceptor, a general type of receptor, would quickly transmit information to my spinal cord that said, hey, this is hot, you need to move your hand away. That's something that, again, would be a general sense. If I walked outside in the middle of February and it was 0 outside and all I had on were gym shorts and a t-shirt to go work out, well, as soon as I walked out there, very quickly, thermoreceptors all over my body would tell me it's cold outside and I need to go back in and put on some more clothes. Okay, so again, those are general receptors. And we have general receptors inside of our body as well. For example, if you have receptors in your gastrointestinal system, your small intestine, large intestine, stomach, those are called visceral receptors. Viscero again means organs, so it's talking about our internal organs. And so those receptors give us input about what's going on with our internal environment. Oh, I've got too much acid in my stomach, and those gastric visceroreceptors are telling me that I feel nauseous at this point from the extra amount of acid in my stomach because maybe something that I ate. So again, we have general senses and we have special senses. Now, the special senses that I want to focus on today are going to be the eye and the ear. And the first one that I want to focus on will be the eye. And from my diagram, okay, we can see that we have this outermost structure, which is the cornea. Okay, corneas oftentimes will be harvested from donors as donor tissue. Okay. Then we have the iris, which gives the eye its color depending on the amount of melanin that's present. Then we have the lens. Okay. The lens is going to have connections called ciliary muscles, which can actually stretch or relax, and that either thickens or thins the lens, and that helps to focus the light that moves through the lens. In this front compartment between the cornea and the iris and the lens, we have a liquidy fluid called the aqueous humor. Okay? That is going to be in the front compartment. Behind the lens, this compartment is entirely composed of what's called vitreous humor. It's a more thick, viscous, jelly-like fluid than what the aqueous humor is in the front. Now, once we get beyond the lens, we have vessels, okay? And these vessels are going to be the central retinal arteries and veins. They are going to move throughout the entire back chamber of the heart, and this back portion of the eye, we refer to that as the retina, and this area where we want light to focus is known as the optic fovea. The optic fovea. In that optic fovea, we've got, and I made it red, those are the cones. They are receptors which pick up color, C for color, C for cones. And then we also have what are known as rods. Rods pick up different colors, or excuse me, different amounts of light. If we don't have very much light, then the rods are not that stimulated. If there's more light, more rods are stimulated. But again, in this optic fovea region of the retina, we have rods and cones. Rods give us the ability to see things in lesser amounts of light, whereas the cones give us the ability to see color. If, for example, you're outside and it's dark, there's no ambient light, you could make out a figure of somebody that's coming towards you, but you wouldn't necessarily be able to make out features, you wouldn't be able to tell what they were wearing, you may not be able to distinguish what color their skin is, so it would be tough to determine very much about the person other than their silhouette would indicate that it in fact is a person. On the other hand, if we have optimal light conditions, you'd be able to make out the color of their skin, their eye color, their color of their hat they may be wearing, their shirt color, their jeans, and so on and so forth. Okay, so again, that's the difference between the rods and the cones in the retinal region of the eye. That information from those rods and cones gets taken by the optic nerve to the occipital lobe of the brain, which is in the back of the head beneath the occipital bone of the skull. Now, the occipital lobe of the brain is going to take that information and process it. Okay? So ultimately, what we're getting is just light and color, and that information gets picked up by the occipital lobe of the brain, by the optic nerve, and it's going to be up to the brain to process that. That's why in some situations our brain can be tricked. Okay, there are various little games that you see on the internet, optical illusions, you know, people may have those in books or something like that, and what is happening is the rods and the cones are picking up information, and they are giving what information they have, differences in color, differences in the intensity of light, darkness, or white light, and ultimately that information is being carried to the occipital lobe of the brain, and the brain then has to fill in the blanks. And that's where there can be some issues about what something looks like. Okay, for example, if a person is outside and it's dark out and they don't have a lot of light to go with, okay, they may mistake something like a Halloween figure on somebody's porch for an actual person and think it's an intruder. Okay, again, the brain sees a figure of a human being, a head, a neck, shoulders, so on, and the brain ultimately takes that information that is picked up by the rods and the cones in the optic fovea region of the retina, and then it's up to the brain to fill in the rest of it with information that it's picked up over the years. You can kind of think of the occipital lobe as being a supercomputer, and it has stored in this supercomputer all sorts of bits of data that have been collected over years and years. Now, if you lived in a dark cave all of your life and had never been out of the light, out into the light, and really didn't have a database built, well then everything would be new to you and your brain wouldn't be able to fill in the blanks. And so what you would perceive would be a very distorted interpretation of what's going on around you. But as your brain picked up more and more information, then when you get just a glance at something, the brain would have more information to help fill in those blanks and ultimately give you the perception of what you're seeing around you in a more accurate view. Now, the ear is going to ultimately do the same thing. What we're going to have is this outer portion called the auricle or the pinna, and it's going to focus sound waves in this case. When I hit this desk, a sound wave is produced, and since I only hit it the one time, a single sound wave gets focused by this large pinna down the auditory canal till it gets to the tympanic membrane. The tympanic membrane is kind of like the drum head on a snare drum. So if I hit the desk one time, the tympanic membrane has one sound wave hit it. The tympanic membrane has what are called the auditory ossicles. Auditory or audio means sound, ossicles means tiny bones. Ossi is a combining form that means bone. The suffix ical means tiny. So the auditory ossicles are tiny bones of hearing. And so we have what's known as the malleus is right up against the tympanic membrane. It's going to be connected to the incus, which is connected to the stapes. Malleus literally means mallet or hammer in Greek. Incus means anvil, and stapes means stirrup. And what's going to happen is the malleus is going to pound on the anvil, the incus, which in turn pulls on the stirrup, the stapes, and that actually causes fluid waves at this part of the inner ear known as the oval window, and that ultimately gives us information that gets picked up by the cochlear nerve in this kind of a snail-like structure called the cochlea, and that cochlear nerve is going to carry that information back to our temporal lobe, and ultimately the temporal lobe is going to make the interpretation of that particular sound wave. Judging from its pitch and its frequency and so on, the temporal lobe scans through its database and can now give us what that noise was. That's something striking a desk, or that's a jackhammer hitting a road plate out on freeway construction, or that's a bird chirping. Okay, but if we had never heard anything, if we had been born deaf and had gone through the first 18 years of our life never hearing anything, and then all of a sudden we get a cochlear implant, our temporal lobe is not going to be able to interpret the sound of a jackhammer hitting a road plate, the sound of a pointer hitting a desk, the sound of a bird singing in the morning on a spring morning. So ultimately, it has to pick up all of that information, make the connection of, oh, that particular noise is emanating from that bird, and save that data for later. So even though later on you may not see a bird, you know what that noise is. Okay? Well, this brings us to bone conduction that I mentioned. And again, this is the tympanic membrane. Sound waves will strike this tympanic membrane, ultimately causing the malleus to pound on the incus and pull the stapes. And as I said, that ultimately causes a fluid ripple in the inner ear, and this fluid is called endolymph, and those ripples are going to be interpreted by the cochlear nerve, okay, which resides in the specialized organ of hearing called the cochlea. The cochlea is going to ultimately give that information to the cochlear nerve, which transports it to the temporal lobe, that ultimately makes the interpretation of what this noise is that is producing the sound waves that's striking the tympanic membrane. So these are our ear and eye, structures that are associated with our special senses, and they give us input to the world around us. So this is the overview for the special senses.